So hi students, so let's carry on with our learning. So what we will do today is we will look at this particular topic on what happens when an electric dipole is placed in an external electric field. Okay, so suppose there is a region in space where the electric field looks like this. So here I have a uniform electric field. So this is a parallel uniform electric field. Now in this uniform electric field, if you put a dipole, so if we have a dipole, so this is a dipole which I have placed in a uniform electric field. Like you know already, dipole will have a charge here plus q and it will have a charge here minus q separated by some distance. Just for ease, let us say that it is equal to 2d. Already we have seen that the dipole moment P is equal to q into 2d. So I can say it is equal to 2 times q into d, and we also have seen that it is a vector going from the negative charge to the positive charge. So let me put an arrow here so that you understand that it's a vector quantity. So, so there is a dipole which is placed in an external electric field. On this charge, on the positive charge, there is a force F which is equal to q into E. On the negative charge, there is a force which will be in the opposite direction, minus q into E. Please note that the direction of the arrows will indicate the direction of force on positive charge. So on the positive charge, there is a force towards the right which is equal to q into E. On the negative charge, there is a force towards the left which is equal to minus q into E. So if you look at this, the net force is equal to 0. So I can say that F net is equal to 0. So the net force acting on the dipole is 0. So the dipole doesn't move. But instead what happens is there is going to be a torque. If you look, if this is the center, this force is going to move it clockwise. This force is also going to move it clockwise. So there is a net torque which is acting on the dipole. And the torque is equal to R cross F. So from there I can say it is 2 times D into F. F is Q into E. So which I will change it to 2 times D QE sine theta, where theta is the angle. Suppose the dipole is this way and the electric field is this way. Theta is the angle between the two. Then you have n cap, because understand that a cross product always gives you a vector quantity. So this is the dipole, this is the torque acting on the dipole. So now 2 times d into q is the dipole moment. So I can say this is equal to P cross E. P for dipole moment, E for electric field. So the net torque acting on the dipole is equal to P cross E. So when a dipole is placed in an external electric field, it experiences a torque. That torque is equal to P cross E. Okay. So if you understand this, the next question that could come up is, what would be the work done? Suppose you have a dipole which is placed in an external electric field and then you are trying to move the dipole. So there is an external electric field here. Suppose there is a dipole which is there here, and suppose I want to turn the dipole by some angle theta. What is the work done? Okay, so already we know that dW or work done is equal to torque d theta, where theta is the angle by which it will be turned. So assume that the initial position of the dipole, this is just an assumption, so depending on the question we have to work it out. Suppose the initial position of the dipole is this way and then you are turning it by some angle. So I can say that the torque will be equal to P E sine theta d theta. Sine theta d theta, and we can integrate it from the initial angle theta 1 to a final angle theta 2. So when you work with it, it becomes PE. The integral of sine theta is minus cos theta. So from an angle theta 1 to theta 2. So when you work this out, you understand that this is equal to P dot E. So this is the work done to turn a dipole by an angle theta. Now, whenever you get questions of this, please understand the value is going to depend on theta 1 and theta 2. So, you have to be very careful. I have just given an indication of what it is. Okay, I have just told you how to go ahead with it. My negative sign remains. The negative sign remains. So, it is going to be minus. So, let me remove it from here. So, it is minus PE cos theta. So, that will be minus P dot E. So, two things. When you have a dipole in an external electric field, there is a torque acting on it. Because of the torque, over a period of time, the dipole will try to align itself in the direction of the external electric field. So, the dipole aligns in the direction of E. So, this is what happens when a dipole is placed in an external electric field. So, over a period of time, all the dipoles will be aligned in the direction of the electric field. Then, if you have a dipole and if you are turning it by some angle theta, then the work done will be negative of P dot E. So, accordingly we can find out what it is. Now here, remember what theta 1 and theta 2 is. It all depends upon the initial position. The position that I have drawn, theta 1 will be 90. So, theta 2 will be whatever angle you want to change it to. So, when you are changing it from this angle to whatever angle, what will happen is that you will not have to do the work done by you will be negative. So, there will be work done by the electric field. So, the electric field itself will do the work in changing it. Now, suppose the electric field was in this direction and the dipole is here, and this is the way the dipole is aligned. This is plus Q minus Q. Then the work done has to be done by the external agent. So, in this particular case, the dipole is naturally aligned in this direction. So, to turn this dipole, you have to do work, and that work will be given by P dot E. So, I was telling you about the work done in moving a dipole. So, initially, if you leave a dipole in an external electric field, it will orient itself parallel to the electric field. So, here the angle is 0. Now, suppose I want to turn the dipole by some angle theta. So, this time I have already explained to you that work done is equal to T d theta. So, torque into d theta will give you the work done. So, from there we got W is equal to P E sin theta d theta. Now, if you are turning it from an initial position 0 to some theta, so this will become theta 1 to theta 2, but theta 1 is equal to 0, so theta 2 is equal to whatever angle. Then when you integrate this, you will get W is equal to, so here again understand, the torque is equal to PE sin theta. So if torque is PE sin theta, as the angle changes, sin theta changes. So as the angle changes, torque changes. So when you want to find out the work done will not just be equal to the torque into change in angle, but it will be equal to integral of that, because the torque keeps changing with time. So when I work this out, it will become minus PE cos theta, and the limits are from theta is equal to 0 to theta is equal to some theta. Let us keep it as some theta. Then what will I get? It will become minus PE cos theta minus PE cos 0 is 1. So when I work this out, it will become PE into 1 minus cos theta. Okay, so this PE into 1 minus cos theta is the work done in turning a dipole by a small angle, by some angle, whatever angle you are turning it. So work done can also be represented as the change in potential energy. Okay, so I can say that work done is equal to U2 minus U1. That is potential energy in the final potential energy minus initial potential energy. In this case, when the situation is here, the potential energy we will say is equal to U1. When the dipole is in this configuration, we will say the potential energy is U2. Okay, so this is U1, this is U2. So now the change in potential energy will give you the work done. So here U2 will be equal to minus PE cos theta. So U2 is equal to minus PE cos theta, and U1 will be equal to PE, negative, both negative. So from there, when you do u2 minus u1, it is equal to negative of pe cos theta minus pe. So now when you take the negative sign inside, it will take this option. Okay. So understand that this is the work done when a dipole is turned by an angle theta. This is provided the initial position is here. If the initial position is something else, we will have to find out. When the initial position is like this, we can say that the initial potential energy is zero. There is no potential energy. Only when the dipole is in this state, we will have some potential energy at any other angle. But in this particular state, the initial potential energy will be zero. Why? Because theta is equal to 90 degrees. Okay. So now when the dipole turns, the dipole will turn automatically. So this is what happens when a dipole is placed in an external electric field. There are two questions that you get. What happens when a dipole is placed in an external electric field? Next question, what is the work done in turning a dipole by an angle theta? So when a dipole is placed in an external electric field, net force acting on it is zero, but there is a torque acting on it. The torque is equal to P cross E, which is equal to P sine theta n cap. Then again the work done is equal to T d theta, the integral of T d theta. So from there we found out the work done is equal to minus P dot E. So remember, P cross E is equal to the torque acting on the dipole placed in an external electric field. Then remember, work done is equal to minus P dot E. This is the work done in turning a dipole by an angle theta. Okay. So I hope I explained to you about this initial position and the final position. Thank you.